Children, next we are going to derive another expression, that is the last portion of this chapter, that is capillary rise. Capillary rise, we are supposed to find out an expression for capillary rise. So you might have studied about capillarity in your chemistry classes. So what do you mean by capillary rise? See, a tube of very fine core is called capillary tube. That means a very narrow tube can be considered as a capillary tube. And when such a capillary tube is dipped in a liquid, the liquid immediately rises in the tube. Okay, so when a narrow capillary tube is dipped in a liquid, the liquid rises immediately through the tube. So this phenomena is called capillarity or capillary rise. In the case of mercury, capillary depression is observed. So in the case of mercury won't rise up the tube, instead mercury falls down in the tube. So this is capillary depression, and whenever a rise is observed in the tube, it can be considered as a capillary rise. Okay, so capillary tube is a very narrow tube, and when such a capillary tube is dipped in a liquid, the liquid immediately rises in the tube. And you might have noticed whenever we dip cloth or something in kerosene or oil, you can see that the kerosene or oil rises through that cloth, or through a wick. Whenever we dip a wick in the oil or kerosene, we can see the oil or kerosene rises through that wick. So such expressions can be considered, such phenomenon can be considered as an example for capillarity. Okay, so we are going to find out an expression for that capillary rise. How much that liquid has risen up in this tube. Okay. So here we have considered one such capillary tube. This is a capillary tube, and this capillary tube, radius of this capillary tube is small a. So small a is the radius of the capillary tube. Okay. Then it is dipped in a liquid of density rho. So this is liquid of density rho, and our capillary tube is dipped in that liquid of density rho, and surface tension of that liquid is S. Okay, so if the liquid has a concave meniscus, you can see. So when a capillary tube is dipped in this liquid, the liquid rises up through the tube, and liquid rises up through the tube, and here this is the liquid level now. So this meniscus is known as the concave meniscus. It is curved inwards. So this meniscus is known as concave meniscus. Okay, and this is the concave meniscus, and it will rise in the capillary tube with a concave meniscus. Let H be the height of the liquid level in the tube. That means let H be the rise of the liquid in the tube. So this is the amount of rise denoted by H. Now let Pi be the pressure on the concave side of the meniscus. So this is the concave. Here also we can consider the same concave meniscus. Okay, in this container also the liquid level can be considered as a concave meniscus. So here Pi, see Pi is the pressure on the concave side of the meniscus. So this is the concave side of the meniscus. So let Pi be the pressure on the concave side, and let Po be the pressure on the other side. So in the case here, if we consider this portion, this is the other side, and here let Po be the pressure. Okay, so let Pi be the pressure on the concave meniscus, and let Po be the pressure on the other side. Now there will be a pressure difference. So the excess pressure on the concave side of the meniscus can be written as, just now we had discussed an expression for pressure difference. What is that? Pi minus Po is equal to 2S by R. So here R is the radius of that meniscus. See, if we complete this meniscus, just complete this meniscus. If we complete this meniscus, we will get a sphere, and let R be the radius of that sphere. Okay, let R be the, so this is the center of the sphere. Let R be the radius of that sphere. Okay, if we complete this concave meniscus, we will get a sphere, and let R be the radius of that sphere. Now, I told you that the radius of this capillary tube is small a, isn't it? So this is the radius of the capillary tube, and let it be small a. And if we join these two points, you will get a right angle triangle here. And let this right angle triangle be A, center let it be O, and let this point be C. So here we have got a right angle triangle AOC. Okay, and what is this angle? This angle is theta, and this is our angle of contact. So what is angle of contact? Angle of contact is the angle between the tangent drawn to the liquid at the point of contact and the solid surface. So here this is the tangent. So this is our liquid. This is meniscus is our liquid, and we have drawn a tangent here, and this angle is the angle between the tangent at the point of contact between solid and the liquid, and also between the solid. So this theta lies inside the liquid. So this is angle of contact. So if this angle is theta, then this angle also will be theta. Okay, so this angle is theta. Okay. Now we can move to our derivation. So here excess pressure on the concave side of the meniscus is Pi minus Pu equal to 2S by R, where R is the radius of that meniscus. Okay, just now we had studied the expression for pressure difference, that is Pi minus Pu equal to 2S by R. And from this right angle triangle AOC, what is cos theta? So this angle is theta. If this angle is theta, cos theta is adjacent side by hypotenuse. So adjacent side, this is the adjacent side AC, and AC is the radius of this capillary tube, that is small a is the radius. So adjacent side AC is A by hypotenuse. So this is the hypotenuse. Hypotenuse is radius R. So A by R. Okay, cos theta is A by R. Therefore, R is equal to A by cos theta. Now, substitute this R in this equation 1. So, when you substitute 2 in 1, you will get Pi minus Pu equal to 2S by, instead of R, substitute A by cos theta. So, we get Pi minus Pu equal to 2S by A by cos theta. Therefore, Pi minus Pu equal to 2S. This cos theta will go to numerator. So, you will get 2S cos theta by A. Okay, so let it be our third expression. Pi minus Pu equal to 2S cos theta by A. Now, let us consider 2 points here, point M and point N. Point M is outside the capillary tube. Point N is inside the capillary tube. Since these 2 points are at the same level, pressure acting on these points will be same, isn't it? Since M and N points are at the same level, pressure acting at these points will be same. So pressure at M is equal to pressure at N. And we know pressure at M is Pi. We had already discussed that. Pressure at M is Pi. So pressure at M is equal to pressure at N. So pressure at M is Pi. And what is the pressure at N? See, pressure at N will be equal to Po. Po, that is the pressure here, plus pressure exerted by this liquid column of height h, and that pressure is equal to h rho g, isn't it? So pressure exerted by a liquid column of height h can be calculated using the equation h rho g, where rho is the density of that liquid, and it is also given here, or it is also known. So the pressure acting at the point N will be this pressure Po plus pressure exerted by this height of the liquid column, that is h rho g. So we can come back to our derivation. So pressure acting at M is Pi, pressure acting at N is Po plus h rho g. Therefore Pi minus Po, bring this Po to this side, Pi minus Po is equal to h rho g. And when we consider these two equations, that means equation 1 and equation 4. Just look at the LHS of equation 4, that is Pi minus Po. LHS of equation 1, Pi minus Po. Okay, not equation 1, sorry children, equation 3. Okay, so just look at these two equations, equations 3 and equation 4. LHS of equation 3 is Pi minus PO. LHS of equation 4 is Pi minus PO. So we can equate the RHS part of these two equations. So when we equate the RHS part, you will get H rho G is equal to 2S cos theta by A. Therefore, H is equal to 2S cos theta by A into rho G. So this H itself is the capillary rise. So we had found out an expression to calculate the capillary rise. And in the case of water, this angle theta is 0. So here we have considered that the meniscus is like this, a concave meniscus, and this is theta, isn't it? But for water, the meniscus will be like this. So here we cannot plot any theta or any angle here. So for water, the meniscus will be flat, so angle theta will be 0. So cos theta will be equal to cos 0, that is equal to 1. Therefore H is equal to 2S by A rho G, or surface tension is equal to, from this S is equal to A rho G H by 2. A rho G H divided by 2. So this is the expression to find out surface tension of water in this case. Okay. So that's all about the capillary rise. It's very important derivation. You must practice this derivation thoroughly. It's very, very important. Okay. So notes of these derivations have been already uploaded in your Google Classroom. Please download the notes file and learn it. Okay children, so with this I am concluding this chapter. Notes of the topic and YouTube video have been uploaded. Just go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.